Hello world. In this video, I will present DeepMTL Pro, deep learning-based multiple transmitter localization and power estimation. This paper is published at a journal, Pervasive and Mobile Computing. I am Kaitao Zhan. This presentation will have three sections. First, the overview. Second, transmit power prediction. And the third, localization with background authorized users. For the overview, this journal paper is an extension of one of my previous conference paper published at WOMO 2021. The title of the conference paper is DeepMTL, and the title of this extension journal paper is called DeepMTL Pro. So from the title, you can see that I am an Apple fan. In the Pro version, the quality of writing is improved. So I remove parts that might cause confusion, number one. And number two, I restructure some parts and stick to a top-down writing style. And the third, I try to answer some more why questions, add more motivation to the paper, and try to tell a more interesting story. What is also in the Pro version is that there are more new content. While extending a conference paper to a journal, the journal requires at least 30% new content. So I added a bunch of content, and the two main parts are, first, I designed a deep learning approach for transmit power estimation. And number two, I designed a deep learning approach for the general multiple transmitter localization with the presence of background authorized users. In the rest of the presentation, I will focus on these two new content. Deep learning-based power estimation. Why we are doing this? Because it is useful. For example, we can estimate the secondary user's power to determine violations, where a violation is a transmitter transmitting at a power above a certain threshold. So how does the power estimation work? There are roughly 4 steps. First, we use DeepMTL to localize the transmitters. Here, DeepMTL is what I introduced in my previous conference paper. Now, given the location of the transmitters, crop the transmitters out from the original sensor reading input image. Then third, we feed this cropped image to our deep learning model, pred power, and get the predicted transmit power. And the final step, for isolated transmitters, this prediction is final. But for the case of close-by transmitters, we do a machine learning-based correction. Now here is a figure of the pred power model. So first is localize using DeepMTL. So now we have the location of the transmitters. Then we crop the image. Here, we crop the image into a 21 by 21 pixel image. Here, the original image is 100 by 100, so the cropped image is a lot smaller. Then we feed this cropped image to the pred power model. So we can take a closer look at this model. There are 5 convolutional layers and no max pooling. After each convolutional layer, the 2D dimension of the data will decrease. So at the beginning, the 2D dimension is 21 by 21. In the end, it will decrease to 1 times 1, which is essentially a single pixel. And the value of that pixel is the power of the transmitter. Fourth, we do a power correction if needed. It is needed when the transmitters are not isolated. Now let's take a closer look at the power correction for close-by transmitters. So first, when there are multiple transmitters close by, the deep learning model, pred power, will likely overestimate the power of a transmitter. Here the overestimation means that we define a delta where delta equals to P prime minus P, where P prime is the predicted power and P is the ground truth. The intuition is that the delta has some underlying patterns able to recognize. So we model delta as a function of some features related to the close-by transmitters. The model we use is the linear regression. So once we can model the delta, we do a correction by subtracting the delta from the P prime, and then we can correct the P prime. Here is an evaluation of the pred power. So we are comparing with the MapStar. MapStar is a work published at my previous IPSN 2020 paper. So we can see that the pred power model with correction is better than the pred power without correction, and it is also better than the MapStar in terms of the power estimation error. Now let's talk about the intruder localization with authorized users. Why we are doing this? Because having authorized users in the background is more general in the shared spectrum paradigm. So assume we know the authorized users information. A simple strategy is to localize all transmitters, including the authorized and intruders, then remove the authorized users. But can we do something new? Do something better? So here is the subtract net model. This new approach tries to subtract the received signal strength at the sensors by a value received from the authorized users. This subtraction is done by a novel convolutional neural network model. We refer it to as the subtract net. So assume we know the authorized user's information, and we encode it with an image, and we have the sensor readings from the area. So we generate the subtract net input by stacking these two images together. So here, the dimension of the stacked image is 2 by 100 by 100. Then we feed this input into the subtract net. This subtract net has 8 convolutional layers, and this model does not have max pooling layer. What it essentially does is that it removes the power from the authorized users. So what is left in the image is the power from the intruders. And this is what the DeepMTL wants. So we feed this subtracted image to DeepMTL, and DeepMTL will give us the intruder locations. Here is the evaluation. So we can observe that when the number of intruders is 3 or more, the new approach, the subtract net, which is the pink bars, will have a better performance than the alternative, which is localize all, then remove the authorized transmitters. Thank you for listening, and for more details, please see our paper at this link provided below the video. Thank you.